So, sort of in the last 5 or 6 years or so, a small community of people have been noticing that certain kinds of stability phenomenon in areas like topology, algebra, geometry, and group theory can sort of be boiled down to constructing some exotic algebraic structure and showing that it has good properties like that. It's highly generated or Noetherian or something like that. And so what I wanted to open up with is 2 examples of that, one from topology related to configuration spaces, and one from algebraic geometry related to secants of Veronese embeddings. And they won't really look at all like each other, but then I'll try to explain one possible framework for understanding these things, this theory of twisted commutative algebras, which I've been developing with Andrew Snowden for, I don't know, at least 4 or 5 years. So I've written up some references here, so there's different parts that I'm talking about, so these papers are referring to different things. So sort of for an introduction to twisted commutative algebras, I see the second article. It's supposed to be an expository article, so if you're interested, look up those articles. Okay? So I think everyone's seated now. Okay, so let's get started. So as I said, I wanted to start with 2 examples. So I guess I'll start here. So example 1. So we're going to let X be a sort of nice manifold. I'll give some criteria in a second. Dimension at least 2. And here, nice, you can add the following adjectives if you like. It's a little stronger than what you need, but compact, connected, oriental suffices. There's a lot of feedback from this microphone. Okay, so for each non-negative integer, I'm going to define the space pconf, denote the following, the n tuples of points in X, which are distinct. Okay, you can just think of this as a subspace of the Cartesian product, so that gives it to topology. There's no space here. Okay, so there's a few things. I mean, this has been studied for a while now, but there are a few different results that I want to illustrate. So, there's a theorem. So this has sort of contributions from Church and also in collaboration with I'll just won't write other names, but E is Ellenberg, F is Farb, and N is Nagpal. Maybe I'll just write Nagpal. Sorry, apologies. I think my writing kind of brushes up against the images. Okay, so there's several parts to this. Let's talk about this first one. So for each I, actually let's fix a field. So fix field F. And if you can't see down here, just let me know. But I'm assuming that this is okay. So for each I greater than equal to 0, the function n goes to the dimension of the ith cohomology of this space, as n varies, the coefficients, is a polynomial function for n sufficiently large. Okay, this is part 1. So, well, this is not exactly a consequence of 1, but it'll be a consequence of sort of the result in the background. Part 2 is that, well, there's a natural action symmetric group on this space, so you can quotient out by that, and you get sort of, this is sort of, you can think of as ordered n tuples of distinct points. You can think about unordered n tuples of distinct points. So if characteristic of the field is 0, then this function is constant. So my opposite symmetric group is actually constant. It actually gets some sort of bizarre behavior in positive characteristic. So if characteristic is positive, then this function is in fact periodic. eventually periodic, I guess. You can say more about it. You can, the period is power of p, or the piece characteristic, and well, there's a lot more things you can say, but let me just keep it simple. Okay, so sort of the history of these results. In a sense, Church was studying this back in maybe 2010, 2011, and he obtained this result by the study of some kind of algebraic structure. And the third one is Nagpal. And his first one is sort of more general. Well, it's not more general, but anyway, let me just leave it at that. Okay, so that's example one. So just to give a flavor of one kind of stability type property that I want to talk about. So that's from topology. What about a different kind of example? So let me move on to an algebraic geometry example. So, well, let's keep this a little simple. So let's say X is a projective variety. And my result's only going to be valid in characteristic 0, so let me just do it now for a field to characteristic 0. Although this question you can ask in general. Okay, so there's two different constructions I'm interested in. So, well, two constructions. So the first is, well, if you have a projective variety, you can kind of Veronese re-embed it. So, with Veronese re-embedding, so what I can do is I can think of X inside of Pn. Let's say the D is Veronese re-embedding. So D here is an integer, positive integer. So I can do the D equal Veronese re-embedding. Won't specify what that is, but what you do here is you just send these coordinates x1, xn to all monomials of degree D in the xi's. Okay, and then you just take the image of X under that out. All right, and the second construction, the secant varieties. So let me do something slightly more general first. So let's say we're given X and Y in Pn. Then I can define the join of X and Y. Well, this is going to be, okay, this is going to be slightly annoying to write down, but let me, bear with me for a second. So I'm going to write X plus Y, where X is in X and Y is in Y. And I'll take the Zariski closure. Okay, so this is a little bit of abusive notation, but what I mean here is, what I mean here is, well, there's an underlying vector space in this projective space, so X and Y range over all representative. So, I think projective space is a set of lines, so X and Y are sort of choose a line and also choose a vector in there, and then add them up, then take the line that they get, and then do that in all possible ways. Okay. And then the secant is defined as follows. So you have the secant varieties. So it's an iterated join of X of itself. So I'll define secant 1 of X to be X, and secant R of X to be the join of X with secant R minus 1. Okay? Okay, and so what I'm interested in is the behavior of secant varieties of Veronese re-embeddings as D is getting large and you're sort of fixing R. So there's two parameters here. So you can sort of, if given these two constructions, you can kind of iterate them in all sorts of ways. You can take secants of X, you can Veronese re-embed them, you can take more secants, you can So, okay, so there's two parameters here, R and D. And, okay, so there's sort of this, meta theorem, which is that varieties, let's say the arithmetic properties of varieties, or the algebraic properties of varieties improve as you Veronese re-embed them. And I won't really make this precise, but there's a few examples you can see as you Veronese re-embed them. And so, well, actually, I was sort of motivated by some work, some related results, but so you can ask as a more basic case, let's take x is equal to Pn. What happens to it, what kind of properties do secant varieties obtain as you let the variance and reembedding increase? And then as a result of this investigation, I was able to get a more general result, so I'll write that down. So this is my work. This is these first two papers. So, well, the first one is this result I'm writing down. The second one's a follow-up, which I won't mention. But so let me write it first and explain a little bit about why you would even be interested in such a result. So, okay, so let's see. Let's fix x, and let's fix an r. I guess positive. Okay, so then the content is that there exists a constant. Well, it's going to depend on x and r, so I'll write it as like that. But there's this constant such that the ideal defining secant r of, ooh, I didn't give this a notation. Okay, so let's call this vd of x. So that's going to be the d-Veronese reembedding of x. Is generated in degrees less than cx of r. And that's independent of d. Main point. Okay, so let me just say a few words about why I was interested in a result like this. So, you know, the sort of community of people who are interested in secant varieties, there's a lot of different reasons for that. There's some kind of tentative connection to algorithms and things like that. There's sort of interest from different kinds of areas of mathematics and computer science. So one sort of basic questions about secant varieties is a sort of a natural construction that comes up all the time in these kinds of areas. One of these kinds of questions is how do you determine if a point lies on a secant variety, right? So if you have a variety which you construct in some kind of extrinsic way, you don't know anything about. I mean, it's kind of not that easy necessarily to understand the ideal that defines it, right? So we define it as just like this kind of closure of these sums, and it's a little hard to work with, but. Yeah, so if you wanted to be able to test questions like, does something that I've constructed lie on the side of the secant variety for like r equals 3 or something like that, one way you could test that is if you knew the equations that defined it, you could try to see if all those equations vanished on it or if there's a single one that didn't vanish on it, and that would give you your answer. So, so there's been a lot of work in trying to understand the equations that define secant varieties. You know, even in some cases like where x is equal to Pn. So here I'm taking just an arbitrary subvariety, but you could even consider the case where x is equal to Pn, and there very little is known. So I mean, there's like various kinds of results, various kinds of techniques, but the general picture is still quite murky. So so I was kind of surprised that I was able to get a result like this. But so that's sort of trying to give some context for why. I mean, at first glance, it kind of looks like it's not really clear why this would be interesting, but yeah. So hopefully that gives a little flavor of that. Okay, let's see how we're doing time. Well, let me pause for a second. So is it okay so far? Are there any questions about these examples? So it is pretty far removed from the topics of this conference, but so we'll quickly move into something more algebraic. I mean, my hope is that, as I said, there's sort of a small community of people who are working on these kinds of stability type questions, and I'm sure that many of you would have valuable input. So if I could get some of you interested in this area, that would be excellent. But we'll see how it goes. All right. Yeah, so maybe it's worth mentioning that here, sort of some inspiration here for me for this result is there was a previous result work of Dreismann Cutler on secant varieties of segre embeddings. So that was sort of I find this work quite interesting. But so there they were working not with various embeddings, but with segment embeddings of products of projective spaces. They use very different techniques to get a very different result. But anyway, so I thought I would mention that. Okay, so let's move on then. So here are just two examples. You know, they don't really look like they're related to each other, but the thing is that there's actually sort of at least in my opinion, there's a sort of common algebraic framework which can be used. Once you sort of get comfortable with this, is sort of behind both of these results. I mean, I'll do a little more work, but okay. So let's talk about that. So this is getting into the algebra. So let's say common features of these. Like how would you even prove results like this, right? I mean, so these are kind of existence results. So I mean, just to give a hint of what's coming up. I mean, basically the idea is that in both pictures, there's some kind of auxiliary algebraic structure which is sort of combining all these examples. I mean, here you have these configuration spaces, and you have one for every value of n. What you can try to do is kind of combine all of them at once and put some large kind of algebraic structure that acts on this cohomology all at once. And here you have many various embeddings, one for each d, and well, you're taking secants of those. But so you have this d that's varying, and again, you can try to put a common algebraic structure which acts on all of them simultaneously. And so the idea is that how do you get these existence results? Well, it's going to be a consequence of some kind of some analog of Hilbert basis theorem, right? So it's just going to be like some structure is let's say either an ideal or a finely generated module or something like that, and these bounds are coming from the fact that there's a bound on the degrees of generators in some suitable sense. Okay, so that's sort of the idea. Okay, so I just said that. Okay. So a possible framework so as I mentioned at the beginning, are these twisted commutative algebras. And from now on, I will just denote these by TCAs. Yeah. So as I said before, if you want to know more about the basics behind this theory, you can look at that's 1209.5122. This is a sponsor article. Okay. So there are many different ways you can give this definition. By trial and error, giving these kinds of talks over the last few years, I feel like this is probably the easiest one to give in a talk. Although in my mind, it's the hardest one to actually work with. So there's that compromise. But since you're not actually trying to prove anything in these next 40 minutes, it matters. Okay, so let's let A be have a positive grading like this. So this is a graded associative unital algebra. Yes. Such that each AN has an action of the n symmetric group. Okay, so we're going to require a few things. So I didn't really start the schematic correct. Let's see. So so this is going to be. I'm going to be giving the definition of twisted commutative algebra. So we're going to start with this graded space, and it has a multiplication such that each AN has an action of Sn and multiplication. So this I'll use mu for the multiplication. So the multiplication from degree n and degree m. So I have this map. This is a graded algebra. So I want a few properties. So this is equivariant for the product group Sn cross Sm. So that acts on this thing on the left. How does it act on the thing on the right? Well, Sn cross Sm you can think of as a subgroup of Sn plus m, right? So I'll just write here this is a subgroup of Sn plus m in sort of the obvious way. And so so Sn cross Sm also acts on the right side. Okay, and one more property. So where's the twisted commutativity? and all right, tau nm x tensor y. Whoops. Okay, I'll just ignore the multiplication. So if I multiply x and y, where x is an and, y is an am, so x is an and y is an am. This is equal to y times x, where tau nm. This is an element in Sn plus m, which swaps the first n elements and the last m elements. I guess the easiest way to write this is probably the following. It does 1 to n plus 1, n plus m. This goes to n plus 1, n plus m, 1, 2. All right, so it just swaps the first n letters and the last m letters. So that's that element. Okay, so let me give you an example, which I'll talk about to make this more clear. That was a bit of a mouthful, though. So at least as all the notation makes sense, like, it's sort of consistent with. I mean, you don't want it to be like confused on just the notation, but okay, hopefully that makes sense. So let me give you sort of the basic example, which I'll quickly move on. So example. So let's like K be like a field. So I said algebra here. I guess I implicitly meant that this should be an algebra over A0, which I'm going to denote by K. So I'll put it here. We'll assume it's a field. You don't need to, but no reason to make it more complicated than it needs to be. Okay, so let's let E be a free module of rank D. And we're going to take A sub n to be the nth tensor power, or the nth tensor power of E. Okay, and the action of Sn is permuting tensor factors. Something I'm sure you're all very familiar with. Okay, so what's the multiplication? Well, concatenation. So mu is usual concatenation of tensors. Okay, so it doesn't look commutative to me. This is tensor algebra, right? But it's associated to unital. It's graded. Each an has an action of Sn. And in fact, well, if you think about permuting tensor factors, multiplication is equivariant for Sn cross Sm. Okay, check. And actually, the last property is if you concatenate an n tensor and m tensor this way, or if you concatenate in the other direction, it satisfies that last axiom, right? So you get this twisted commutative. You don't get a commutative algebra, you get a twisted commutative algebra. Okay? So you can check all axioms satisfied. Okay, so I'm going to give this a name. So I'll call this, for reasons I won't really go into, I'm going to call this sim E bracket 1. Okay, and so maybe it's worth pointing out that these are, this is generated degree 1, generated degree 1, and in fact every twisted commutative algebra generated degree 1 is a quotient of one of these algebras for some choice of E, for some sort of D, I guess. All right, any questions about that example? Yeah?
Are the graded pieces of A always finite dimensional over A not?
Sorry, are always what?
Finite dimensional vector spaces.
Well, I mean, in complete generality, you don't need that, but
Okay.
yeah, you can really do whatever you want. It's pretty general. So maybe I should, as a historical remark, I should say, so where does this definition come from? So, like I said, I've been working on these gadgets with Andrew Snowden for the past 5 or so years, but they'd appeared much earlier in the homotopy theory literature. Well, but not the twisted commutative algebra, but this sort of variant called twisted Lie algebras had appeared, maybe sometime in the 70s. So, and possibly they were around even earlier than that, but just some kind of things are hard to track down. But okay, so so this is kind of algebraic structure, which actually, in fact, this will govern this example 1 when you take E to be one-dimensional, and it doesn't exactly govern this one, but you have to kind of do a little bit more. But the basic idea is that these algebras are responsible for this result also. Okay. So let me say a little bit more about them. So, and in fact, these algebras are not of interest themselves. It's really the module categories that are the main players. So the interesting thing will be to prove good properties about their module categories and show that these modules exist in nature. So example 1 is these cohomology groups of these pure configuration spaces are example module over one of these algebras. So any property you prove formally about these modules, you can get for free. Well, actually, I guess the key input is actually finite generation, but I'll get this in a second. Okay. So modules. So the definition will be a little similar. So we're going to have M, which is the direct sum, again, over non-negative integers. And each, I'll just write it like this, Sn acts on Mn. And we assume and again, this is equivariant. This multiplication map is okay. So that's the definition, and then whatever the usual axioms are. So there's also this associativity axiom that you have, but I don't know, we'll drop that. Okay, and then the key definition we'll need is that M is finitely generated. Well, there's sort of a naive definition you can make up, and that's what I want to use. So I just want to say that there's finitely many elements that produce everything else using the operation of addition, multiplication under A, and action in the symmetric group. Okay. Say x1 through xr that generate I'm using I don't know, the A module structure, Sn actions, addition. Okay, great. Maybe I'll keep this up for a second. Okay, so like I said, we're interested in these module categories. As is, it's pretty difficult to work with these modules. I mean, it's a very complicated definition. It turns out that for these special class statistical algebras, and more generally actually, but you can give very simple functor category descriptions for the module categories. Okay, so we have simple models for models for module categories. Okay, so I'll just do it for this example. So I'll define a category as follows. Define category, we'll call it Fi sub D. So the D is the same as that D over there. As follows, the objects are finite sets. Okay, all finite sets. And morphisms are defined in a slightly funny way. So morphism from morphism from a finite set S to a finite set T consists of two pieces of data. So one, you need an injection from S to T. And two, you need a sort of, don't really know how to motivate this, but you need a coloring. So this is a function g from t minus the image of s to the numbers 1 through d. If d equals 1, that last piece of information is extraneous, and then you just get the category of finite necessity injections. But otherwise, you need this. And so intuitively, this is supposed to be, the set 1 through d is supposed to be indexing a basis for e. Okay, and again, so actually I didn't really say the result yet, but so so the point is that the category of sim E1 modules is equivalent. Okay, yeah, I guess it's fine. So everything's over, this ground ring K. But okay, so I didn't really state that explicitly, but so as equivalent to the functor category functors from Fi sub d to K mod. Okay. So in many ways, this second definition, functors on this sort of reasonably explicit category Fi sub d is a lot easier to work with than this other one. Okay. And well, I guess all of you are familiar with functor categories. All you can try to transport all the different notions of submodules and quotients and kernels and all that stuff over to this setting, so you get an abelian category. Well, I guess it's also probably clear from this definition, but so we have that. So like I said, intuitively, this coloring is supposed to be it's supposed to be reporting the action of various monomials in this tensor product. That's sort of, I won't really explain why this is true, because it'll just eat up more time than I have. But okay, so there's that result. So we have to probably have to say something non-trivial about these if we're going to do anything with them. So let me state basic results. In the title we have this Noetherianity property. So let me state a Noetherian property that these models, this model category satisfies. Okay, so the theorem. With sort of many contributions, the history's a little bit mixed up, but okay. But in any case, the following papers certainly contribute to this. I guess I'll actually put it in here. So it's the same authors here: Church, Ellenberg, Farm, and Ackball. Earlier work of Snowden by himself, and then joint work of myself and Snowden. So I'll just put SS. So let's assume K is Noetherian. Well, if you're assuming it's a field, that's fine. But like I said, you can assume that to be any community of ring you like. But let's assume it's Noetherian. Okay, then submodules. Maybe I want to. I guess this is fine. Submodules of finally generated Fi modules are again finally generated. I.e., this category is locally Noetherian. Okay, so this is a familiar property. Well, why might we care about this? Okay, here's another thing that's worth saying. So if K is a field and M is a finally generated FID, maybe I won't state that result. But okay, so there's a result you can say for general D, but since I'm only going to use the case D equals 1 in this talk, let's say it's a finally generated Fi sub 1 module, then, well, you get a polynomiality result like this. So the function n goes to the dimension of K of M evaluated on any set of size n, but we'll pick this one, is eventually polynomial. Okay, so you can sort of see where this connection might be going. The point is that you can define an FI model structure on this cohomology, which I'll explain in a second, and then you use this first property to show this finally generated by deducing that property from some easier to understand models. Okay. So how does that work? So going back to example 1. So here's a sort of maybe more functorial way to write this. So I say X is a topological space, and S is a finite set. We'll define this pconf Sx to be this space of injections S to X. Okay. And if you find a bijection from S to 1 through n, it's exactly that space over there. And so this is a functorial with respect to injection. So this gives a contravariant functor, variant from Fi sub 1 to topological spaces. And hence, it gives you, if you fix a value I, it'll give you a covariant functor to, I guess, F models here. So for each I, get functor, let's say, I guess I'll just say Fi module. S goes to ith cohomology of pconf Sx with values in your favorite, well, anything really, any commuted rule. Okay. And so the key point is that under some suitable assumptions on X, like here we have a manifold dimension at least 2 with some properties, one can use various techniques to show that it's finally generated. The key point here is a sort of certain spectral sequence of Totaro, and the whole point of understanding this locally Noetherian property is that, well, if you do computations of the spectral sequence, you have to take kernels, and if you start with something finally generated and you have a kernel, you want to guarantee that's also finally generated. So one way to do that is just to guarantee that's always true for any submodule. And so that's sort of how that all connects. Okay. All right. Being in time. Great. Yes.
What goes wrong in positive characteristics? Because you have a statement that's in positive characteristics.
Oh no. So the first bullet point is valid for any field. It's just when you pass to the quotient space, you can identify cohomology with the invariance, and then taking invariance is exact and characteristic 0. So that's how you get the statement about the unordered configuration space and characteristic 0. In positive characteristic, you need to know something much stronger about these modules in positive characteristic, and that's work on that call. But I won't get into that. But not enough time. Okay. So there's about 10 minutes left. Let's see. So, like as I said, this thing about the secants, it's significantly more involved, and there's not enough time to talk about this. So let me just write a sentence. So this is example 2, the secant case. More involved, and it uses a category which sort of contains FID for infinitely magnetic RGD. I won't really get into that, but infinite. These D's are basically the dimensions of certain, well, it doesn't matter. But so you get some much larger category, but the idea is sort of similar. You prove some locally Noetherian property, and then you show that this ideal, well, the collection of all ideals of these secant varieties as you vary over the Veronese embeddings is an ideal in some ring, and then you use some finite theorem, and you use the Hilbert basis type theorem. Okay, so that's how it works. And maybe I should also say that. So, and this also extends. In a sense, you could. I mean, this definition of this secant variety. Well, it was fairly geometric and hands-on. So, but you can actually make it a purely algebraic definition of it. So you can. This really extends to arbitrary, more general commutative rings. You can talk. I mean, in a way, once you've set up the algebraic definition, you can talk about secant ideals of any graded commutative ring. Makes sense. I mean, it doesn't really matter for the perspective of this this technique. So you can do that. You can also get results on syzygies, not just ideal generators. So these first two articles I mentioned in the first line. The first one is about the result I wrote down about the bounds and ideal generators. The second one is some follow-up, which kind of does this more categorically and gets results in syzygies. Okay, so maybe I'll end with hopefully, I mean, you know, my perspective is that like the connection here is these categories are fairly concrete, and you can sort of think. I mean, if you like, I mean, this is kind of maybe not a great way to think about them, but you can think about them as, you know, infinite quivers, right? Like you can, instead of thinking about all finite sets, you can just think about, you can choose one representative, so just choose one set of each size, and then you get a bunch of arrows between them. And there's many relations, so that's sort of why, I mean, in my mind it's maybe not so useful to think about them as quivers, but there's many relations, and so you can think of these quiver representations for the infinite quiver. Yeah, but somehow the techniques you need are, you know, quite different. As you can see, even this question of Noetherianity, when you're dealing with finite dimensional algebras, doesn't really even make sense. I mean, you wouldn't ask that question, but once you get this infinite setting, it does all of a sudden make sense. So let me give you one last example where we kind of know something about it, but not very much. So, I should say there's a lot left to do. You know, this kind of this area of acoustic algebras is, we know very little. We know something about these things general degree 1, but beyond that, there's sort of a zoo out there. All right, so here's one more. I'll try to define this in as quickly as possible. But so there's some open things. So I'll just say sort of maybe the simplest thing that's open that we kind of know how to do. So let's define A sub n to be k bracket, okay, also set of perfect matchings of the set 1 through n. Okay, and so this bracket notation just means take the free k module spanned by this set. So this is okay, so this is only relevant when n is even. So perfect matching here, I mean, write your set as a disjoint union of two element subsets. So it is only non-zero when n is even. Okay, and so there's an action, there's an obvious action Sn here, and you can multiply them by concatenating, right? So can multiply by concatenating perfect matchings. Okay, and so this is an example of a TCA general degree 2. And from here you can already see that the behavior is quite different. So those which are general degree 1, we saw with these tensor spaces and they had exponential growth. This guy has super exponential growth. So this sort of theory is quite different from maybe the classical theory of commutative algebra, where, you know, the degrees of the generators of your algebra are really kind of immaterial in many ways from the perspective of the algebraic properties, but here it makes a big difference. Okay, you can check this general degree 2, right? Because any perfect match you can get by concatenating and then permuting the points. You can mix them up in any way you like. Okay, so what we showed, so this result, so this is the last thing I'll write down. So I'll write down the names actually. So this is joint work with Nagpal and Snowden. So what we're able to show, and that's this last paper I wrote down here, 1501. So so A is so A modules, right this way, are locally Noetherian, meaning again that submodules of finite generator modules are Noetherian, provided that if K contains a field of characteristic 0. Okay, so we can prove this because we use sort of a lot of intricate representation theory of, I guess in this case it's orthogonal groups, but the techniques sort of don't really extend to many other examples, and in any case don't extend to positive characteristics. So a basic question: is this true, more generally, even say K equals F, FP? Even if you assume it's a field, let's just make it simple. So there we don't even know where to start. So I sort of think this is the first case where if you're interested in this kind of business, it's probably the first place where there's something we kind of know how to do, but not really. And there's other reasons to care about these more complicated examples. We'll just say in words, it's related to sort of secondary stability results in topology that's kind of ongoing work of Jeremy Miller and Jenny Wilson. But I think it's a good place to stop.
Any questions, Georgie?
In the last example, if you would put AN to be the division of the step into set of characteristic V.
Yeah.
This will fit Noetherian?
No idea. So that's something we generated in degree 3, and there we know nothing about the modules. We know something. Well, not me personally, but so Harm, so Harm Dirksen and along with Andrew Snowden and Robert Egermont have been working on that algebra actually. There's a sort of more geometric perspective, and so you can talk about the sort of spectrum of that algebra, and what they show is that that top-level space in Noetherian. So there's some progress there, but it's pretty far from this statement. So at least there's some work there.
Okay. Further questions, comments? Not the case, and let's thank some guests.